We now find gravitational potential at a point due to a solid sphere. So let this circle represents a solid sphere. Now m is mass of the solid sphere, r is radius of the solid sphere. Now suppose we have to find out the potential at the point P. This point is lying outside the solid sphere. So we can imagine the solid sphere to be made up of large number of concentric cells. Say this is M1, M2, M3, like this. Now we can find for each shell potential at this point P. Now suppose for mass M1, for mass M2, for potential because of this shell M1 will be equal to minus G M1 by the distance of this point from the center of the cell, that is this distance is A. Because of this concentric shell of mass M2, this will be minus G M2 by A. Likewise, so potential being a scalar quantity, total potential will be equal to the sum of all this potential, G M1 by A plus minus G M2 by A, and so on. So therefore potential is minus G by A common, M1 plus M2 plus M3, like this. So that is mass of all the concentric cells. This is nothing but the mass of the solid sphere. So thus potential at any external point due to a solid sphere is equal to minus G mass of the solid sphere by A. Similar way we can, if we keep a point mass equivalent to the mass of the solid sphere here, and we find the potential at P, then also the potential becomes minus G M by this distance is A. So thus we conclude that to find potential due to a solid sphere at any external point, we can imagine the mass of the cell to be concentrated at the center of the cell. This is minus Gm by A. This is case 1 when the point is lying outside the solid sphere. In next video we will determine what happens when the point is lying on the surface of the cell or inside the solid sphere. So even if it is lying on the surface of the cell, then also the potential on the surface, on the surface of the cell, then also potential will become equal to minus Gm by A means what? The radius of the cell. Here only the distance of the point from the center of the cell equal to distance of the point from the center of the sphere equal to the radius of the sphere. So this will be the potential at a point on the surface of the solid sphere. Case 3. What happens when the point lies inside the solid sphere? Suppose this is the point. Here we have to find out the potential. Now to find potential at P because of the whole solid sphere when the point is lying inside the solid sphere. So this case we can imagine the solid sphere to be made up of two parts. One is the inner solid sphere of radius A. So for this, let us suppose V1 is the potential, plus we can imagine the outer part of this solid sphere, this part having a thickness, this thickness is R minus A, and this is made up of large number of concentric cells. So suppose potential due to this outer concentric cells of thickness R minus A at the point P is V2. So therefore potential at internal point P will be equal to the sum of these two potential. Now we will find individually the values of V1 and V2. So we have now V is equal to V1 plus V2. Now V1 is potential because of the inner solid sphere of radius small a. See, density of the solid sphere is m by 4 by 3 pi r cube. This is the mass per unit volume, that is 3m by 4 pi r cube. So the mass of the inner solid sphere is, volume is 4 by 3 pi a cube into the density of the solid sphere, that is 3m by 4 pi r cube. So this 4 pi cancel out, 3 cancel out, so this becomes equal to m a cube by r cube. This is mass of this solid sphere, therefore the potential because of this inner solid sphere is minus g. M, mass of the solid sphere, is m a cube by r cube by the distance of this point from the center of the cell, that is a. So this is minus g m a square by r cube. Now to find V2, that is potential because of this outer shell, let us imagine an elementary shell here, say at a distance of r. Let dr be the thickness of this elementary shell. This is dr. Now we will find potential at this point because of this elementary cell first, then we will integrate this from this point to this point, because the cell is lying between this distance, this to this point. So what will be the mass of this elementary shell? So to find the mass of this elementary cell, we have to find out the volume of this elementary cell first. So therefore the mass of this elementary cell is 4 pi r square into dr. This is the volume, and density of this solid sphere is 3m by, this is 3m by 4 pi r cube. So this becomes equal to 3m r square dr by r cube. This is the mass of the shell. Now we know that the potential at a point inside a cell is equal to, say, let it be dV2. This is minus g, mass of the cell, this is 3m r square dr by r cube, minus gm by the radius of this cell r. So this becomes equal to minus 3 g m. This r cancel out, r dr by r cube. So potential at this point we found because of this shell, this is dv2 we found. Now if we integrate this from a to the radius of this cell r, then we will get the total potential because of the outer part, outer thick concentric cell, that is v2 is nothing but integration of dv2, the integration of minus 3gm r dr by r cube, and the limit is from a to r, so this becomes equal to minus 3gm by r cube. Integration of r is r square by 2, a to r, so this is coming as 3gm by 2r cube, and this is r square minus a square, so this is the value of v2. Now we got v1 here, this is the value of v2. Now if we put the values of v1 and v2 here, we get v equal to, v1 is minus g m a square by r cube, plus v2 is minus 3g m, this is g m by 2r cube, r square minus a square. So by summing up we get this value as minus g m by 2r cube 3r square minus a square. This is the gravitational potential at a point inside the solid sphere P, which is situated at a distance a from the center of the solid sphere.